Section 9.3 is about modular arithmetic, and modular arithmetic gives us a tool that can help solve many problems in a fairly easy fashion. The basic idea behind modular arithmetic is if you pick a counting number other than 1, so we'll pick 3, that every single natural number when you divide by 3, so pick some natural number and divide it by 3, it'll go in a certain number of times, but what will the remainder be when you divide by 3? That's the critical question. What will the remainder be? And the answer is the remainder might be 0, in which case 3 goes into the number. And we can see numbers where that's true. 3, 6, 9, 12, 15, etc. Those are multiples of 3. However, the remainder might be 1. 3 might go into the number, and almost exactly, but it might have a remainder 1. So, for instance, 4 is such a number, and 7 is such a number, and 10 is such a number, and 13 and 16, etc. But when we divide some number, some counting number, by 3, another possibility is that we could get a remainder of 2. So those are the numbers like 5 has a remainder of 2 when you divide it by 3. So does 8, so does 11, so does 14, so does 17. And this list of numbers keeps on going. Now backtracking, we get some very important numbers, 2, 1, and 0. Those belong on this chart, but those are really important. They're so important that they make up a set of numbers which helps us work in something called modulo 3. These three numbers, 0, 1, and 2, helps us work in modulus 3. And every single counting number, whether it's 72 or 95 or 86, every single counting number has one of these three remainders. And so one thing we could do is we could say, okay, what does 29 have as a remainder when we divide by 3? And instead of writing down what is the remainder when we divide 29 by 3, 29 mod or modulus or modulo 3, 29 mod 3 is equivalent to what? And so we could continue this chart over here in 18, 19, 20 and figure out where 29 is, but the simplest thing to do is to take 29 and divide it by 3. 3 goes into 29, I don't know, how many times? Seems like 9. But what's the remainder? The remainder's 2. So which of these three columns is 29 going to be in if the remainder when we divide by 3 is 2? Well, it's going to be down here. It's going to be in this column somewhere, because these are the numbers in this column that have a remainder when you divide by 2. So we know that 29 mod 3 is equivalent to 2. So what do you think 28 mod 3 would be equivalent to? Well, if 29 is here, I'm guessing 28 is going to be 1 over, and it's going to have a remainder of 1. But we could do 28 divided by 9, and it would go in, 28 divided by 3, and it would go in 9 times, and we would have a remainder of 1. So let's go on. What would mod 7 look like? Well, it's remainders when you divide by 7. What kind of remainders could there be when you divide by 7? Those are the remainders. You can't get a remainder of 7 when you divide by 7. So the remainders are 0, 1, 2, 3, 4, 5, 6. So what about the remainder of 0? These are numbers that 7 goes into evenly. And these are numbers that 7 almost goes into, but there's a remainder of 1. and so on and so forth. And I think that you can see that this table is fairly easy to fill out, because all the numbers go somewhere in the table and they all go in order, and it doesn't really take much effort to do this, although eventually we would like to be able to work on problems without doing this much writing. So mod 7 starts out this way, and if you have some number like 345 and you want to know that mod 7, what it's equivalent to, what's being asked is, which one of these numbers is it equivalent to? Which one of these kinds of remainders does it have? And yes, you could count down here all the way to 345, but it would be much, 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 much better to simply do a division and find out for yourself. So it's a remainder 2, so that means the 345 is going to be down here somewhere in this column that has a remainder of 2. Do you see how that works? Now we can use that idea to help us solve problems. So what kinds of things have 7? 0 through 6 is 7 numbers. What kind of cyclic things have 7 in them? Well, days of the week come to mind. There's 7 days in a week. So let's make up kind of a random sounding problem. Today is a Thursday, let's say. So what day is Thursday going to be? Well, we got to assign days. So let's assign this Sunday. So this will be the Sunday class. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So anytime we in this remainder of 4 group, we're thinking Thursday. So today is a Thursday. Which Thursday? Well, it doesn't really matter. Let's choose this one. So we're in the remainder of 4 group. 61 days from now, from today, will be a what? Well, 61 days from today will be one of these days of the week. Will it be Friday? Will it be Saturday? Well, we could start here and start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, blah, blah. I don't want to do that. So when we add 61 days to day 4, we get 65. So we are going to land on the 65. The question is, where is the 65 down here? Which class does it belong to? Well, what's the short way of finding out which class it belongs to? The short way is dividing it by 7 and seeing. So it belongs to the remainder of 2 class, so that means it's going to be a Tuesday. That's kind of interesting. I sort of like that. Let's try another one. Let's say today is Thursday again, just to have something to say. And let's say 1 year from today is what day? And there's no fancy stuff, no leap years or anything like that. So the question is, how many days after this Thursday, which I'm choosing this for, how many days after this Thursday would it be? Well, there's 365 days in a year, so we could start here and we could count 365. I don't want to do that. We're going to land on the 369 number. The question is, down here somewhere, when we take this chart all the way to 369, 369 is going to land in one of these 7 spots. The question is which one? And the answer, as always in this section, is a clever division, and you find the remainder. The remainder's 5, so the remainder's 5 means it's in this, which means it's going to be a Friday. So that's just pretty fun. That's pretty interesting. The above technique that we used with days of the week can be used for an awful lot of problems in math contests, specifically junior high math contests. The following problem is kind of a well-known sort of problem. It occurs in a lot of these exams. And it goes sort of like this. You pick some convenient number like 7, and you do 7 to the 403rd power. That is 7 times 7 times 7. That's a lot of 7s. It's an enormous number. But you don't want to know the entire answer. What you're asking the person is, what's the last digit of the answer? The very last digit. And so I'd like you to look at this. 7 to the 0 power ends in 1. 7 to the first power ends in 7. 7 to the second power ends in 9. 7 to the third power ends in 3. 7 to the fourth power I didn't feel like writing down, but it ends in 1. 7 to the fifth power ends in 7. 7 to the sixth power ends in 9. 7 to the seventh power ends in 3. And so 7 to the 0 power ends in the same thing as 7 to the fourth power, which ends in the same thing as 7 to the 8th power. So all of these, when you take 7 to each of these powers, they all end in 1. That's kind of like the Sunday, from Sunday, Monday, Tuesday, Wednesday. And all of these powers, 7 to the first, 7 to the fifth, 7 to the ninth, etc., they all end in 7. 7 to the second, 7 to the sixth, 7 to the 10th, they all end in 9. And 7 to the third, 7 to the 7th, 7 to the 11th, they all end in 3. So the question, to answer this question, what is 7 to the 403rd power end in, you got to figure out where 403 is going to fall. Is it going to fall here somewhere in the first column, which means it ends in 1, or here, or here, or here? And so how do you do that? Well, you take 403, and this is kind of like base 4, not base 4, modulus 4, modulo 4. So what we're going to do is we're going to divide this by 4. And when we do that, we get a remainder of 3. 4 goes into 403 100 times with a remainder of 3. So 403 will be eventually in this column right here. And all of these types of numbers, when you take 7 to the 3rd, or 7 to the 7th, or 7 to the 11th, or 7 to the 403rd, you always get 3. So the answer is, it ends in 3. Pretty cool. Let's go through some problems. The answers need to be mod 3. So 4 plus 4 is 8. You divide 8 by 3, the remainder is 2. 7 plus 11 is 18. Divide 18 by 3, the remainder is 0. 6 plus 10 is 16. Divide 16 by 3, the remainder is 1. Here I was too lazy to add up all these and then divide by 3, so I divided by 3 first. This divided by 3 is something, and the remainder is 0. This divided by 3 is 5, and the remainder is 0. This divided by 3 is 2, and the remainder is 2. So I've written down the remainders for each part of the sum and then add those remainders and get 2. 12 take away 14 is negative 2, so I simply added 3. You can add as many 3's as you want in mod 3 without ever changing anything. So negative 2 plus 3 is 1. 7 take away 2 is 5. 5 divided by 3 goes in once, remainder 2. Didn't want to multiply all this out, so I divide the remainder here when I divide this by 3, and the remainder is 0. So I have 0 times 7 plus 5, which is 5, and the remainder when 5 is divided by 3 is 2. In mod 3, I can add as many 3's as I wanted to this, and so negative 7 plus 0 is the same thing as negative 7 plus anything that is 0 mod 3. I chose 3 3's, or 9. That is 0 mod 3, and so negative 7 plus 9 is 2, and I'm done. In a problem like this one, you are simply solving an equation. You're trying to figure out what makes this true mod 7. And for now, the thing you ought to do is just try each of the mod 7 basic numbers 0 through 6 and find one that works. For instance, in this problem, if you put a 6 right here, you will get 4 times 6 is 24, and mod 7, you get a remainder of 3, so 6 is the only number that works. 6 is the solution to this equation.